Okay, we are going on the recording, and it is a substitution lab for computational chemistry 476, Chem 476. So we do have an ambitious plan to cover several practical skills in computational chemistry, and just going off record. Okay, I'm going to log into the cluster. There is a very famous and helpful trick of mutual equivalence of using either small simulation cell and many k-points, or simulation cell consisting of several unit cells and then using one k-point. So in this respect, I am going to offer a little trick of how to double the size of the simulation cell. So since this directory contains very helpful, good results, I'm going to keep it as is and do anything else in the new directory. So I'm making directory. So there I will expand the simulation cell twice as bigger. So it was C2H2, one unit cell. Now I'm going to prepare a model that will explicitly contain two unit cells, C4H4. So I will call it C4H4 periodic. Created directory. Now I'm going to copy there the output of this calculation. So I'm copying the there contcar and immediately renaming it into the postcard. So please look at this. Be attentive. So the contcar means continuation. So if you finish one job and want immediately continue, so you rename contcar into postcard and restart job. If you want to keep the old results, then you need to place this new postcard into a new directory. Okay? And now I am going to copy their other three critical files: incar, podcar, and keypoints. And now I myself, I am going to this new directory. So I'm going cd c4h4 periodic. What do I have? 4 files ready to run, but our postcard has only one unit cell, 2 carbons, 2 hydrogens. I want to expand it in the x direction. Let me offer a trick. So I'm renaming postcard into P0 and file P1. So right now there are 2 equivalent files, P00 and P01. Now since the fractional coordinates I have values from 0 to 1, they will stay inside the box. But if you take values of fractional coordinate more than 1, it means that I will place atoms outside of the box. So I'm doing VI P01, and so I want to shift all atoms by the size of one unit cell. So I'm adding 1, 1, 1, and saving. Okay. Now I am going to convert these P files into XYZ and merge them together and then convert them back into the postcard format. So cont wasp to con wasp to con P00 going off record and returning in a second. Okay, so this command wasp to con converts the postcard into another format. See, it is a record of success. Number of types of atoms, writing component. Those file types for WASP, they're a little different, less standard, and they are not included into Babel, although new versions of Babel may include. Okay, so I'm doing the same command with P01 that we have shifted. Now I'm doing second command. Con to XYZ dot PL P00 converted into P00 XYZ. Now the same for P01 XYZ. So let me express curiosity what is inside this file. So more P00.xyz. It is the file that we haven't touched. You see coordinates of the carbons and hydrogens belong to the range from 0 to about 2 angstrom. What can we see in the P01 XYZ? You see all positions are shifted by the size of unit cell. So carbons and hydrogens are shifted by more than 2 angstrom, consistently, all of them. Now, we are going to remove old postcard, but we are going to build new postcard out of these two files. So we know the nice command cat, which doesn't have anything common with the friendly pet, but it is concatenate. So we do cat P00.xyz bigger postcard.xyz. Enter. Well, postcard.xyz may be not the best. Let's call it sort xyz. Now cat P001 into sort xyz. More sort. You see, it's just a merger of these two files. Now let's actually sort into postcard.xyz. Okay, so we had original file, a shifted file with unit cell, merged them together, and sorted so that everything should be in ascending order. Vi postcard.xyz 44 CCC HHH. So total number of ions is not 4 but 8. Then we need empty line. Then we need to start the listings of Cartesian coordinates, and this generated with, we do not need it. Okay, so we are indicating that we have 8 records, 8 atoms, then listing all carbons, all hydrogens. Colon, write, quit. And from now on we can process our postcard as we used before. So rotate XYZ, 0, enter, 0, enter, 0, enter. Done. Now, ting to wasp postcard underscore rotated postcard. Let's try it for the experiment putting 0, 0, 0. And now we do see that the size of the cell is 2.72. Do we believe that it is the right number? How do we check it? We should look on the size of the unit cell of the original file, which is 2.48, and there is no doubt that the size of 2 unit cells in x direction should be equal to size of 1 unit cell multiplied by 2. So we take 2.42 multiplied by 2. Just in case I have lost the skills of arithmetic. So 4.84. Quit. So the size of the unit cell in x direction should be 484. But when we select 0, 0, 0, by definition this code sets up, here are the true sizes of the cell, but it brings it to the 4 just to avoid too many too dense matter. So in order to, we need 484, so, and we need to add 0.84 to the 4, and here we can use our standard 77. So you see where is vector 1, 4.84, head postcard, on along x-axis it is 4.839999, which is as good as 4.84, and there are 8 total atoms. Okay, in case we duplicated unit cell at least twice, we can return to the old-fashioned approach to the k points and use gamma point again. This is questionable, but for educational purposes it is not a bad approximation. So if you have more than one unit cell, it is okay to run it with less k points. Okay, our simulation cell is ready. Let's check. Postcard, k points, podcar, incard. And just to save time, I'm going to do something I shouldn't do. So we please never run jobs on the front node. These will not be tolerated. Here it is, this demonstration is only for demonstration purposes, for just very quick very quick demonstration, but in what follows, we are going to do it in the right way. So I'm typing share apps, name of the account, name of the code, binary, and name of executable. Enter. So it starts calculations. So these numbers that are progressing are self-consistent cycles of improving total density and improving total energy. Let me decrease the font. At the beginning of each series of cycle, it reminds us what are the numbers. So if you see here, N, E, DE, DEPS, NCG, RMS, RMS. So the first column, N, is number of cycle. E is total energy computed at each cycle. DE is difference in total energy at each cycle, and DEPS is difference of the difference. So if this difference arrives to a very small number, about 10 to minus 5 electron volt, well, it is not super small, but relatively small, then the calculation is terminated and system is considered as to be complete. So these cycles over self-consistent energy are repeated once, and as soon as it converges, the system updates geometry. So there are two self-consistent cycles, one inside another, energy, electronic and ionic. So at ionic cycle number 28, the geometry has converged with minus OT. So if you run this job, if you prepare similar input files, let's check if you have the healthy out car. The beginning looks promising. Tail out car. Yes, it tells time report, which means everything went good. So based on this output, you can generate density of states and report. But now we need to go on for new things. We are going to learn how to plot molecular orbitals. I prefer, just from experience, there are no serious requirements, but from experience, I'm trying to run any job in the separate directory. Otherwise, it will be a complete mess very soon. So now I would like to keep working with this polymer C4H4, but I'm going to make another assignment. I want to compute orbitals. And while doing another assignment, it may damage the outcome, which I do not want. So therefore, I'm making directory, calling it with the same atomic composition, periodic, but then I'm making index part charge for molecular orbitals, or how they are called on VASP language, partial charge densities for orbitals. Now, I am copying the cont car from here, so it is optimized geometry, to this new directory, and I'm immediately calling it pos car. So we want to continue from the geometry where we stopped. Optimal geometry, good geometry. And I also want to copy there the key points, plot car, And I do not want to copy in car because I am going to set up something completely different. It will be a new file. But instead, I would like to copy there the file wavecar. So the file wavecar is an analog of the .chk in Gaussian. It contains orbitals. There is another important piece of information that we can learn from the outcar of our ground state calculation. So number of electrons, 20, and number of bands. Number of bands, 15. And if we do well, we can do just tail minus n outcar and look for the last section of the outcar file. There we do see a list. There we do see the list of orbitals. Band energies. So we do see that there are 15 orbitals, and on the VASP language they're called bands. So it is reasonable, since we have 20 electrons, 2 electrons per orbital, the orbitals from 1 to 10 are completely filled by electrons, so they have occupation 2, and orbitals above do not have occupation. Okay? Now, what I'm going to do, I just need this number 15. So I'm going change directory C4H4 periodic part charge. We have 4 files, but for this specific job of orbitals we need 5. We need in car. You see, we are missing. So we need to copy a template file for plotting orbitals from /bin/in_car PC. So this directory contains template in cars, and we rename it with some extension. And here we rename it into simple in car and copying it into this directory. Done. Now let's look inside. What is this specific in car for? Plotting molecular orbitals, quantum orbitals. Well, there are several keywords like partial density, but what is important? What is important? The keyword n bands. So right now n bands, it is number of orbitals, and this was probably from some very big model for 1200 orbitals. We are much more humble in this educational modeling, so n bands equal 15. Another important segment of data is, let me highlight it, E int, so energy interval. So we need to set up the energy interval in such way so that we include so that we include orbitals of interest. So we can do maybe from -10 to +2 to go for several orbitals above and below the HOMO-LUMO. I'm going to VI in car once more. And I'm going to go to last line and modify this E int values. So from minus typing letter I for insert, from -10 empty space +2 colon right quit. Right now we are ready to run another type of VASP calculation, which is equivalent to form check and cube gen in the Gaussian. So I am running VASP code, but with very different input files, right? So it is important that it tells reading wavecar. The wavecar file was read successfully. Good sign. If something would go wrong, it would stop at this point. And then see, it shows band number 6, band number 7. So it generates files which are very similar to cube files for the orbitals. Let's look into this file. ls-lt. You see, there appear files that we haven't seen before. Par chg.0014 ALLK. So those are molecular orbitals in Concha universe. And we are interested primarily in HOMO and LUMO, which would be orbital number 10 and 11. So what I'm going to do, I'm going to go to SIGBIN, making directory C4H4 periodic for church. Go into this directory and downloading I'm going to download all files that start with common. We start with PAR, secure copy from the cluster to local computer. Typing the password and waiting for files. No? Wrong name. Let's try this one. Okay, the files are being transferred. Okay, now they are on a local computer. We still have the open VASP view, but we can close it and reopen it once again with the new file. So remember, this was charge density for only 1 unit cell, but computed with 4 K points. Now I'm closing. I do have VASP view on this local computer. I'm typing bin VASP view, and I'm interested in partial charge number 10 because it will be the HOMO. Entering. Waiting. Hoppa. Not bad. It does appear. So the model appears. Now what I'm doing, I'm going to menu options. I'm going to white orthographic. Now I'm going to bounce, no, not bounce, view, and changing it from 1 to 0.4 to make it bigger. Now I'm going to atoms, which are too large and too ugly, and I'm decreasing their diameter to, let's say, 0.1, too small, 0.2. Okay. Now the gray clouds that represent partial charge density looks too coarse grain, so we can increase the quality. Going to high. See, the images look a little better. And finally, I can change the value of either surface to have it a little nicer. Also, I do not need this slice. I can remove it. And now we can do the, if you want to support the idea that it is a periodic cell, you can look onto several more periodic images of the scene itself. Okay. So those of us who have chemical background can formulate this orbital on the language of pi and tell whether it is bonding or anti-bonding type of orbital. So number 10 is a HOMO orbital. It is very reasonable to make a print screen and copy this image into your PowerPoint slides. Okay? Now, what if you want to see next orbital? LUMA. Instead of running it again, I can just type here in the upper right window the number of new orbitals. You can enter, and you see at the lower left, it is loaded. Unfortunately, I need to repeat some of the settings. Let's see how does it compare to what we had for HOMO orbital. It is a different orbital. So this is a very important skill. From now on, you know how to draw molecular orbitals in VASP. Please, there will be homework to plot orbitals with VASP view software. This is pedagogical. This is not, for most of the papers, there are better pieces of software that create better visualization, but we need it for getting better with the concept of periodicity. So what is an alternative way to plot molecular orbitals? There is a command CEG to cube that we can apply to the any parcharge file. For example, parcharge 10, which corresponds to the home. So this script asks whether we have which type of file we have. So 3 means parcharge, and then it wants elements. So first were carbons. Number of carbon is 6. Second in the list was hydrogen. Number of hydrogen is 1. And then so what do we have? S minus RT. We do have file that has extension cube. We can wonder whether it is the same type, same style files that were similar to what was generated by Gauss view. Let's check if this file can be read and interpreted by Gauss view. So we're executing GV, practicing patience for not very long. Waiting. And here we do have our model. So Gaussian doesn't show whether it is periodic or not, but what we can do, we can go to results, surface contours, surface action, new surface. Opa! See, Gauss view allows to draw orbitals from what? Please let me focus your attention on the very important feature. Typically, when we were drawing orbitals for the isosurfaces, for the isolated molecules, all isosurfaces were represented spheres, represented maybe not spheres, but closed surfaces, without holes, without sharp edges. Like all cans were closed. And now it looks like they're cut at the edge, which means that this is not the end of the story. The molecule is periodic and the orbital is protruding further to the left and to the right along x-axis. So this is an important feature not seen in other models. So Gauss view can be also used to draw orbitals of periodic systems. I'm going to complete this unit of new information, and when I will go for recording next time, we'll go over computing and plotting absorption spectra based on output from WASP software. Now I am going off record.